This lesson is for Calc BC on slope fields and Euler's method. Let's begin. So you pronounce slope fields as an AB thing, but Euler's method is definitely going to be a BC thing right here. And you pronounce it as Euler's, not Euler's. Going through this, what is a slope field? So differential equations, they have like the dy dx or y prime thing in there. Slope fields are going to be kind of a graphical representation of that, because differential equations aren't just like one curve on a graph. It's like it could be anywhere, because it's kind of like just what the slope would be at every point. So you know how like you have to like find the general solution, particular solution. The general is like a plus c. So it's like it could be any graph. You don't know the particular one. So the slope field lets us represent that. And the way we do this on a graph is by like writing the slope everywhere. So just as a reminder, if you have a slope going up, this is going to be positive slope, or dy dx. If you have a slope going down, that's negative. If you have a slope that's straight across like that, your slope's going to be 0. And if you have a slope that's up and down, this is like undefined or going 1 divided by 0. So if you have a slope that comes out to the undefined, we're going to do a vertical line. And what if you had like 0 over 0, something indeterminate form? That's just going to be no slope at all. It's going to be a dot. All right. So let's take this differential equation right here. Dy over dx equals negative x over y. And I'm going to plot from, I'm ignoring this example. I'm just going to plot the lines from 2 to negative 2. And so it's at every integer spot, we're going to write the slopes. So you can make a table. If this was really complicated, you could do a table on the side. And let's say, let's pick my first point. Let's go x is 1, y is 1. What would dy over dx be, or y prime? Should have wrote it as y prime. Well, that would be negative 1 over 1. So that's just negative 1. And right here, I'd make a negative 1 slope, which is about a 45-degree line going down. So just, a little tick mark like this. It should be negative. Now, let's say if I pick the point 1, 2 right there. I'm just going to pick that. And that would be negative 1 over 2, so negative 1/2. Now, that's going down, but it's going to be a little bit shallower. So maybe I'll do that. It's a little shallow. You don't have to be perfect. What if I did, let's take this point right here. If I did 2, 1, well, that would be negative 2 over 1, or just negative 2. So that's going to be a steeper going down. So maybe it looks like this. Other key points right here, like let's see, I took the point 1, 0. So I took the point 1, 0, I'd get negative 1 over 0. This would be those undefined things. So we're going to do a vertical line right here. So every time in this case I divide by y, I'm going to have a vertical line. So actually all of these would be vertical lines right here and right here. Now let's take the point 0, 1, right? 0, 1 right here. So this would be negative 0 over 1, so just 0. And that means it's going to be flat line. So in this case, every time x is 0, it's going to be a flat line. And if you kept going, you'd fill in these things. Like this is going to be negative 2 over 2. It would be the same slope as this. In fact, all of these would end up matching. So, and then you'd get like, oh, if I had 1 over negative 1, this ends up being positive 1. So you'd start filling out these slope fields. This one would be a shallow 1/2. This one's going to be positive 2. This one's going to be negative 1/2. This is going to be negative 2. That would be like a 1 there. This would be like a shallow. Okay, I'm not doing a perfect job. If you had 0, 0 in the middle, so if I went 0, 0, I have 0 divided by 0 undefined, so there's no slope in the middle here. Now, you look at what's going on here, and you're like, oh, do you see a shape kind of forming? And you might see this, because it kind of looks like a circle. Like in the way it kind of works, like put your cursor anywhere, and if you followed the curves, it could look like a circle like that, or a circle like this, or any of those circles that I'm drawing perfectly. And here's what it would look like. If you kept going, you get this kind of thing. Now, what's a neat thing? Let's say if we did differential equations. So I do dy over dx equals, was it negative x over y? Okay, if I did finding the general solution, if you remember how to do this, I'm going to multiply by y on both sides. Multiply by x on both sides. I get a dx on both sides. And then you antiderive both sides. You'll get y squared equals negative x squared plus c in a case. And if I move that x over here, I'd get y squared plus x squared equals c. You're like, what's this equation? Well, you might remember, what's the equation of a circle? X squared plus y squared is equal to r squared, and r is just a constant. It's the same thing. So yeah, this is like the equation of a circle. Not a function because it doesn't pass vertical line test. And this is just the differential form of this. There you go. Other neat things. So, okay, I could ask you, I'm not doing that kind of stuff today. Things that might be on an AP test is multiple choice questions like this, where you get this. And if you want to pause and try it, you can. But I'm going to go over the answer. Which of the following differential equations might match right here? I like playing this as like a elimination game. So I like, look at your tick marks here. One thing I would notice, all these tick marks, they're all positive. They're all going up. This is like going up way, way more up here. And these are going up way, way more. And these are kind of like halvesies right here. Sometimes I'll look for like if there's any flat slopes or vertical slopes. Those are kind of indicators. Or I might just pick a point. And the easiest point in the world is, let's take 0, 0, 0. So if you plugged in 0 for x and 0 for y, you get a slope that is positive. Now, I don't know if it kind of looks like it's halvesies. Maybe it's a positive 1. Maybe it's a positive 2. Maybe it's a positive 1.5. It's hard to tell that, but I know it's positive, right? So like, you don't need to know exactly, but let's see what kind of matches. So if I put in a 0 for this, I get, let's say if I tried 0, 0, 0 at A, I get my y prime would equal 0. Well, that'd be a flat line. This is supposed to be a flat line, so that's not going to work. So I can eliminate A. Same thing with B. If you plugged in a 0 for the y, you're supposed to get a flat line right here. It doesn't work. C would be 0 minus 0. Again, another flat line. No. So it's a lot of eliminations like this. I think that's the best way to approach. Now I'm up to 50-50. And I go, if I plugged in a 0 here, I'd get a 1. And if I plugged a 0 here, I'd also get a 1. So right here, both of those work. So now I can try other points and see if it makes sense or whatnot. But it could be tough. One other thing you can look at, so you can keep trying more points until you find one that eliminates one of these. One thing I might notice is that, hey, everything in a line, everything in a horizontal line is the same slope. See that? All the horizontal, everything in the same row, I guess we call it, row is the same slope. So one thing that indicates to me is that it's only changing when the y value changes. When x value changes, it doesn't change. Like you change an x right here, it's still staying the same. So if I know it's got to change with y value only, my answer is D, because this involves a y. And this only involves an x. That's one little thing that could help you eliminate, but it's about eliminating answers. This problem is a little different. So slope field for a certain differential equation is shown in the right, which the following could be a specific solution. So these aren't like it's different from this. These are differential equations. These are like the specific. It's like they anti-derived them, right? So look what the slope of this graph looks like. It could be like this. It's kind of looking like this, where it's like going super steep on this side, and then it kind of flattens out. So what graph, and like these are all potential specific solutions. Which of these functions looks like that? And to do that, you're going to need to understand what these functions look like. And this is a, you don't know this, like, this is a good thing to practice. What does e to the x look like? Hopefully, you know, that's a parent function that goes up like this, the exponential function. And natural log of x. You might know what that function looks like. It kind of goes up like this. It's got an asymptote right here, right? Perfectly drawn lines. I love this. I'm doing this with a mouse. Now, what are these other ones? So if that's e to the x and ln of x, if I do a negative e to the x, what does that do to the graph? Putting a negative right here, this is going to flip it, mirror it on the x-axis right here. This just flips it upside down. So what I would have for d of x is going to be this graph. That's what my d is going to look like. But I'm still going to have this asymptote right here. So you might say like, oh, this curve kind of looks like that because we're going like this curve and this curve don't look like this. So I can eliminate e and a. But this curve kind of goes down. It kind of looks like this, but this doesn't have an asymptote right here. So that's going to be my issue. So the next thing I'm going to look at is B and C. So in B right here, if I have a negative x, this is actually, okay, let's go C. So negative e to the x, again, I'm going to flip this on the axis. And I'm just going to look like, on the x-axis, and it's going to look like this. So it's not C either. It actually is going to be B, because B's graph, when you negate the x, it actually flips it on the y-axis, and it'll like mirror it, on the y-axis right here. So looking like that. That's a matter of knowing what those functions look like. Euler's method. I like this Patrick JMT's video, so if you want to see a better one, go watch his. But let me do this in 4 minutes. Hey, Euler's method. So if I need to construct an approximate solution for this one, here's the thing. Euler's method is about approximating a differential equation. You're approximating what the graph kind of looks like. We're trying to get to some y value in the graph, and we're using a differential equation. We're given information like what's the start point and a step size usually, or where do we start and where do we have to go. And the key part that I understand how to do this is just make this table. X, y, dy, dx, and delta y, which is equal to the slope, which is just dy over dx. I don't know why they don't write that, times delta x. Because the concept behind this is the change of y over change of x is how you find the slope, y2 minus y1 over x2 minus y1. We can say this is approximately equal to dy over dx. Euler's method is a way to approximate a solution. And because these are approximately equal to each other, we're going to, and then like rearranging the math on that a little bit, lets us get equations like this. So here's how this works. We're going to start at a point. And this is where I start with my xy, so 0, 1. My goal is to keep going across and keep doing steps until I get to y of 0.3. So 0.3 would be down here, and I want to find this y value. One thing to notice here, my delta x is 0.1. So that means my x value every time I go down is going to go up 0.1. Just like this. Now, I'm going to work across. So if I know my first case, 0, this is 0 and this is 1. dy dx, you plug in, well, dy dx equals y, so I'm just going to plug in 1. So that should be equal to y. And my delta y will be my slope, 1 times delta x, 0.1. So my delta y is going to be 0.1. Now, so x changes by delta x every time, 0.1, 0.2, 0.3. Y changes by delta y every time, but the delta y changes. So this y is going to be 1.1. Because I'm adding so it's going to be 1 plus 1.1. 0.1 to get 1.1, okay? Now, let's do the next one. This is going to be 1.1 because it just equals this y. So this is going to be 1.1 times 0.1 still. So that's going to be 0.11. Now I'm going to add 0.11, this guy. So it's going to be 1.21. 1.21. Okay, 2, 1. Gosh, I gotta, that class starting soon. But I'm gonna do this. I'm gonna do this in time. 1.21. Now, this would be 1.21 as well. So it's gonna be 1.21 times 0.1. This is gonna be 0.121. And then I'm gonna add in 0.121. So I should get 1.331. I feel like I did that math differently in class last time, but there I go. That's how you do that kind of problem. Thank you, folks. We'll do more examples in class, or go watch Patrick JMT. He's really good.